Dimitri, and thank you for the activity, which I'm really enjoying this series. It's getting into some of the gory details of the methods. And I've tried to be quite neutral in organizing this talk, in that I'm not trying to advertise it as I might to an outside audience, and I'd like us to be, as frank as possible about the shortcomings of some of the methods that we're using, even though we might not say that in a more public kind of environment. But anyway, that seems to be the spirit of the series. And up until now, the discussions have all been very valuable, and so I've tried to keep the talk short. I've only got 40 slides or so, so that we'll have a good chance for discussion either by interrupting or at the end. So I've listed the main collaborators here from a number of different locations. I've highlighted the two postdocs that are currently in our group at Brookhaven, Anna and Long, and I'm mainly talking about their work in this talk. So all of the results are there's a few published results, but most of them are in the submission stage of papers. So they're really live results that are coming out. And then Tadessa was a postdoc up until December last year. Ji-Cheng is a current student in London, and he's involved in every single experiment we do, as well as doing his own studies, and some of his data are appearing in the talk. Anna was a former student in London whose work I'm also going to show, and Jesse was a former postdoc, and I think most of you know the name because he developed the package, the MATLAB phasing package that many of us are using, and I'll talk a bit about that as we go along. Ross and Wansuk are the primary people running the beamline where almost all the data that I'm showing has come from. And Pavel and Shinjay are two names maybe not so familiar. These are computational scientists, and they're involved in some of the new methods that we're developing with the collaboration of the Computational Science Initiative at Brookhaven. In fact, Long's postdoc is in the CSI department, which is a computer-oriented department of Brookhaven. Okay, so my slide didn't advance. Oh, there it goes. Okay, so what I'm going to cover, I'm going to mostly talk about nanocrystals, but I will talk about the extension of the methods beyond that. And I'm going to, the centerpiece is going to be talking about the phasing methods themselves, but I will give an overview introduction to why we're interested in the physics and chemistry of nanocrystals. And a lot of that is to do with the strain which we see through the complex density functions that come out. So the new data I'll show are on strained palladium nanocrystals, and then I'll talk about half the time on some of the new machine learning based methods that we're working on quite rapidly and making very good progress on, that I hope you'll appreciate. Okay, so the methods aren't completely new. I like to set the clock back a little bit at the beginning and say that Bragg himself developed and published a paper in Nature in 1939 called X-ray microscope. And he, along with all of us, appreciate that there's a simple Fourier transform relationship between the diffraction pattern of a mineral here and the image of where the between the diffraction pattern and the image of where the atoms are. And he, not having computers in those days, came up with the clever idea of using an optical transform to turn a diffraction pattern into an image. And so the diffraction pattern is shown on the left. Hopefully you can see my pointer. And he had the machine shop drill a little plate with holes proportional to the size of the structure factors of the Bragg peaks that were measured from this mineral. And then put it into an optical projection system to take the Fourier transform, and what comes out is the Patterson function, the correlation function. And because the mineral has a heavy atom in it, calcium, you see a big peak at the origin of the reciprocal space, and then all of the little side peaks are the positions of the silicon and the magnesium inside the mineral as a correlation function. And that's the raw data, well, the optical image that is interpreted down here. So this was an early version of an attempt to do imaging through diffraction. Okay, so with nanoparticles, the structures are actually very interesting, because when you take away the need for translational symmetry in an infinite crystal, you can get a lot of quite exotic new structures forming. So this is a calculated sort of phase diagram for gold. We do a lot of work on gold nanocrystals, and gold, as everybody knows, is cubic, and it melts at 1200 degrees with a simple melting transition up here. But if you go down to small sizes, there are stable structure and an icosahedral structure, and possibly some others as well. And then the boundary between the liquid and the solid starts to become complicated, because when the samples are this small, in the few nanometer size, they're mostly surface, and so the surfaces start to take over the properties of the materials, and the melting point comes down, and the structures become sort of richer and richer. Okay, that can also be seen just by simple powder diffraction experiments. This is a classic paper from Mittermeier's group in Stuttgart, where they looked at a series of different nanoparticle preparations and just measured simply the lattice constant and plotted it in one direction, and they measured the width of the powder peaks, which gives you the size of the particles. And if you plot it versus the inverse of the size, you get a nice straight line here. And the straight line fits this simple principle, which is that there's a surface tension which is leading to a compression of the crystal given by the bulk modulus, and the relationship is just linear. The coefficient that explains the slope here is just the value of the surface tension, and it comes out to be 2 newtons per meter for palladium. So we get a compression of the average lattice constant of the crystals as we make them smaller. Now, if you look at a more realistic picture of a nanocrystal, it has an equilibrium crystal shape given by the Wolf construction, where the energy of each direction is different, and so you get a preference for some directions having facets and others not having facets. And you typically get a mixture of flat facets and rounded corners in the shape of a nanocrystal in equilibrium. And wherever you have a curved surface, because of what I just told you, that you have this Gibbs-Thompson pressure difference across that curved surface because of surface tension. And so you have a compression that will be expected to be localized at the corners. And if you put in the numbers, the number I just gave you, you would expect to see a phase shift of order a fraction of a radian for the phase that we're going to be looking at later on in the images of the crystals. So this is a measurable deformation of the crystal due to its shape. Okay, so as Dimitri said, we've been working on this a few years. I've got a photograph over there. Where should I put that one? Okay, so I traced it back to about 2003 when we first started running the 34IDC beamline at Argonne. This was about the sort of beginning date of the sort of systematic study of these things for us. And the idea is pretty simple. You just take a powerful synchrotron beam and throw most of it away to keep just the coherent part, about 1% at APS. In max 4, the number is higher because the coherence of the machine is better. But anyway, these are rough numbers. And then you put your nanoparticle in the beam, dimensional data, so you have to put some quite precise rotation axis on it. And then you just measure the diffraction pattern. And oops. And Oh, there we go. And there's no reason, once you've made the beam coherent, you can't focus it to match the size of the crystal. And so some of the latest designs for beam lines to do this are going to consider using zoom lenses so that you can zoom the coherent beam to whatever size matches the crystal that you're interested in the best. And it's hoped that we can get down to really small crystals using these kind of methods. Okay, so when you do that, the way you know that you've got a coherent beam is because instead of getting, if you've got a powder of nanoparticles, instead of getting continuous powder rings from them, you see the discrete spots coming from each individual crystal. And when you can separate them properly, you can see the fringes around each of the spots. And the fringes are the sign that you have coherent diffraction from the nanoparticles. And then if you rock the sample a fraction of a degree, you can get the three-dimensional diffraction pattern nanoparticles. Lost my cursor, there it is. Sometimes if you have too many particles, they run into each other and you can't cleanly separate them, and you just, the easy solution is you just dilute the samples until, or just find a region where you've got isolated crystals and then just concentrate on those. But there is always an issue that you are picking individual crystals, not looking at a proper average, but that's just the nature of the game. Okay, so now to the phasing. This is the picture I always show for how the phasing works. We know since many, many years that there's a simple Fourier transform relationship between a diffraction pattern and the structure of the crystal. And in this case, it's the shape of the nanoparticle which gives these fringes, where two opposite facets of the crystal lead to interference and gives you a fringe spacing in the diffraction pattern. So every flare that you see in the diffraction pattern corresponds to a facet direction of the crystal. And to make a reconstruction of this, you need to find out what are the phases of the diffraction which are not measured by the detector. And so you can't just go inverse Fourier transform to get the object. You have to go around a loop instead in order to get to an image. And in order to make the loop do something, you can overwrite the measured amplitude of the diffraction pattern on the reciprocal side. But when you come to real space, you have to update it as well. And the key there is to introduce a support, which is this box that the particle has to live inside, that cuts off the outer regions of the image and forces the method towards a consistent solution. So the language that's often used, I'm going to actually spell this out, is that we have a real space constraint, which is the support in this case, and a reciprocal space constraint or a modulus constraint, which is the measured amplitude of the diffraction pattern. And you force these against each other in an algorithm, and that's called an iterative algorithm to solve the phase problem. And this is what most of us have been using up until now. Okay, so Stefano Marchesini wrote a very nice paper 13 years ago looking into some of the details of this, and it's got this nice language which is the projection onto sets. So there is a constraint set in mathematical language which corresponds to the observed amplitude of the diffraction pattern. That's called the modulus constraint. And there's a second constraint, which is the support constraint, which is the idea that the crystal has to fit inside a finite volume of space. And that gives you the fringe diffraction pattern that comes out. And it's easy to show that if the object sits inside a certain size box, then there is a maximum spatial frequency of the fringes that comes out, and you can measure the data more finely than that. So you can overdetermine the problem by oversampling the diffraction pattern and measuring more points than the minimum. And the solution of the problem, of course, is the intersection of these two sets. And the way the algorithm works is you start with something that agrees with the diffraction pattern, and then you apply the support, and that projects you onto the other set, but takes you away from the agreement with the diffraction pattern, and then you need to come back. And so this sort of simple picture shows alternate projections onto the support and onto the modulus constraint, and they zigzag, eventually reaching the intersection here, which is the common solution. The problem, I don't have a slide, I'll come to the problem in a moment. So there's a number of algorithms based on this, and the mathematical language is that it's an algorithm, so it's an iteration where the update, the next generation or the next iteration of the image is given by a real space and a reciprocal space projection operation on the previous iteration. And so when Pn and Pn minus, so rho n and rho n minus 1 are the same, then you can say you've converged. And a number of the algorithms that were already there's quite a rich choice of algorithms, but there's a number of different ways that people have proposed. And the one that I've used the most, and many others, is this one invented by Phenup in the 70s, where you apply one operation when the object is inside the support, and you drive it away from the solution if it's outside the support. And the parameter that says how aggressively you drive it away is this beta parameter, which is anywhere from 0.7 to 0.9 or so. And this is one of the things that you can play with in the algorithm to try to make it perform. But anyway, Stefano evaluated all of these, and I think he advocated this one at the end as being the best, but it's all a little bit subjective because every problem is different and every kind of data is different. And so he optimized an algorithm for the problem he was looking at, but it doesn't necessarily work for everybody else. Okay, and so the key to the failure of the method is that the solution of these, the sets are not convex. And so there are many places where, even though they don't necessarily both agree with each other, the modulus constraint and the support constraint come close to touching, but they don't actually touch each other. And so there are multiple solutions where the two constraints get close together and then go apart again. And these result in local minima for any of the algorithms. So if you use the simplest algorithm, just the straight projection method, then depending on where you start, this is Stefano's idealized sort of picture of what's going on. This is a sort of chi-square plot in parameter space, and the global minimum, the lowest minimum, is this one over here, but there are other local minima by construction here. So depending on where you start the algorithm, you end up with ER just dropping into the local minimum, and you don't always find the global minimum. So what the HIO does is, if you start over here, it takes you towards, but not exactly to, the local minimum. It shoots beyond it, and you can. It's like a billiard ball in a potential minimum. It tends to sort of spend most of its time near the best of the minima, the one with the biggest capture radius or whatever. And so it does get you to the right place, but it doesn't actually get you to the bottom of it, because it's always going beyond the correct solution and driving it away from the solution. So what we've happily decided to do is to do mixtures of HIO and ER, using the HIO to get near the local minimum, the global minimum, and then ER to get down to the bottom of it. And that's a very short summary of lots of years of work that many people have been playing with. Now, one more method that Jesse developed, and I have not actually used very much, but many others have, is called the guided HIO method. I'm only putting this in just to just to label it. It was invented by C.C. Chen, who's now a professor in Taiwan. He was a postdoc, I think, with John Miao in UCLA, and proposed this guided HIO method. Jesse picked up on it and built it into the MATLAB phasing program that we use. There's actually quite a few pages of parameters involved in it, but there's two key things to this method. I'm not actually going to say a lot about it because I haven't got as much experience as many others with this method. It does work quite well, and it does give often much better solutions than the ER-HIO kind of method. So it's a genetic algorithm where you start with multiple random sets of numbers, and you pick the best of the, you run it for a relatively short amount of time, 200 iterations typically, and you pick the best solution after 200. You then take the support from that best solution and restart with a new generation of new random numbers with that new support, and then you run that through for 5 generations, and then you end up with a best solution. And as far as I can tell, it's still not a it depends on the data, of course, but even with quite good data, you don't always get an identically the same solution. You still get small variations of the answer in the local minimum, probably driven by the you get local minima that are all very close together that are connected to the noise in the data. The other innovation which is quite important is this low resolution idea. This comes from crystallography, and the idea is that if you've got if you're far away from a solution to a problem, you start with low resolution data and then expand. And so the way Jesse built it in was to put in every generation, he increases the radius of the data which is included in the reconstruction until after 4 generations it uses all the data, and so it gives you hopefully the best solution. But the idea there is by using low resolution data you have fewer local minima, and so you can find the best one more easily. Okay, I'm not actually going to say any more about guided, but I would welcome in the discussion about that. Particularly, I'm a little bit intrigued whether the guided method in computer science has any connection with the machine learning type approaches that I'm going to talk about later on. Okay, so here is HIO ER running with a simple box support for a nice high quality gold nanocrystal diffraction pattern measured at 34 ID. And you see a nice image of the gold crystal coming out with nice facets and rounded edges as advertised. And then the other part of it, which is actually very important for the science, is that the images are complex. And in general, unless the diffraction pattern happens to be locally centrosymmetric, there will always be some symmetry of the diffraction, which leads to an image which is generally complex. And the interpretation usually is that the phase of the image that comes out, which is used here to color the boundary of the isosurface of the gold crystal, is an indication of the deformation of the crystal. And that comes through this picture where if you move a piece of the crystal, you shift the diffraction from that local region by an amount given by Q.U. And therefore, in the image, you would expect to see this shifted block of material coming out with a different phase from the rest of the crystal. Okay, and that was used very nicely by Jesse in this image of a calcite crystal, where you can see dislocations that are associated with the growth of the crystal, where the phase wraps around the dislocation line and has a phase wrap, which is given by the product of the Burgess vector and the Q vector. All right, so now we're going to start looking at some of the new results. This is work that Anna took charge of and has almost got accepted a paper that's been undergoing review looking at palladium crystals. These were grown by Frank Sung at Boston College using a rather interesting two-step method, because we call them nanocrystals, but they're actually 300 nanometer sized crystals, and the strict definition of nano is below 100 nanometers, but 300 nanometers gives us a nice strong signal, so we can measure quite detailed images for the crystals. Okay, so I've lost my, here it is. The particles were coated with alumina in a special deposition technique to try to stabilize them against beam-induced motions, and that seems to have worked, because we are getting the SEM sees through a little bit the alumina, and you can sort of see the palladium forming a sort of octahedral shape inside in the SEM. But when you do the BCDI measurement, you get these nice fringes in the direction of the facets, and you can see the very nice octahedral shape that comes out for the crystals. And we were a little bit worried by this strong phase feature that occurs in the middle of one of the 111 facets of the crystal. But Anna persisted with it and was able to actually understand that, and it's actually quite interesting. So if you cut the crystal open, these are cross-sectional views through the crystal. The Q vector is this 111 going off to the right. At the top here, there is a block of material with a strong negative phase down here. So there's a strong strain associated with that blue feature that was sticking out of the facet in the middle there. But also there's a quite strong opposite strain associated with the edges of the crystal, and this is true in all directions. So there's like a cylindrical structure where it can seen best perhaps in this picture C down here. The middle of the crystal is pressed in the negative direction, and the outside of the crystal is pressed in the positive direction. So there's a cylindrical deformation of the crystal, which is not expected. And she was able to model it by doing a finite element simulation, and I'll show a bit more on the next slide. You can import the shape of the crystal into the COMSOL package and then apply forces to it by construction, and then look at the deformation that comes out and compare that with the phase of the image that we get. And you can see with a bit of work, she was able to get a good agreement with this negative center and the outside positive displacement. Ignore the strong features here. That's to do with she put a cube of material with a different lattice constant in there in order to introduce the strain. But actually, I should tell you the answer here. We can identify this block of material which is causing the strain as the seed that was used for the growth of the crystal. So when Frank made the samples, they did it in two steps. They grew small seed crystals by one precipitation method, and then diluted them and put them into a growth solution in order to make the large palladium crystals growing from the seed. And it turns out, we've seen this in several of the images that we've got, that the seed doesn't go to the center of the crystal. It goes to the edge of the crystal in the middle of one of the 111 facets. So what is happening is the crystal is growing a little bit asymmetrically from the seed that's put in there, and the seed shows up in the final image as this pattern of strain, which is distorting the crystal. And this seed type growth is actually quite important. You get a lot of things like core shell structures, and quite often, in fact, in SEM pictures, you can see in the literature that the seed is at the edge of the crystal, not necessarily in the center of the crystal, as would sort of naively be expected. So this was an interesting outcome. So if you look at the simulation, these are now cross sections parallel to the 111 facet, which is the one where the seed is sitting. You can see the experimental phase and the model are actually quite agreeing quite well. We didn't try to do any fitting of any kind, but we did play with the amount of distortion so that we could get a good agreement. This red is wrong because it's coming from the specific distortion that she included at that location. But the outside of the crystal is responding in a quite interesting way that is explained by the picture of adding a seed to the object and leading to the strain that comes from that. We also looked at the sample as a function of hydrogen exposure, and that pattern of strain, which if you just plot a line running from one corner to the other corner of the crystal, you can see you've got a nice sort of V-shaped strain pattern. It's quite strong. It goes beyond 2 pi. We have to do phase unwrapping to be able to see that properly. But we get this quite strong linear strain pattern due to the presence of the seed twisting the crystal in the way that I just showed you. But when you add hydrogen, the extremes that are the most strained react first with the hydrogen. And so you get this as a function of dose. You find that the strain starts to reverse and progresses towards the middle of the crystal from the outside in this quite interesting way. So we can actually watch the formation of the hydride starting at the edge of the crystal, moving towards the center of the crystal, identified by this strain picture. Okay, so this is now older work. This was Anna Standarte's work that was done at Diamond, but she studied gold nanocrystals during iron deposition, and we were trying to look at the formation of a gold-iron alloy, and we got very good images of this as a function of time and deposition dose. And if you look at the cross sections of those images, this was published in 2018, but we didn't give a proper explanation of where the strain came from. But you'll see that after 2 doses of iron, we've got this very strong cylindrical pattern where we've got a core which is moving in one direction and the outside which is moving in another direction. And we could not come up with any kind of sensible alloy structure that would give rise to that. So if we go back and look at these data, I think we can now say probably what is happening. And that is that after the second dose of iron onto this crystal, it exceeds the solubility of the experiments done at 300 degrees in a surface diffraction beamline. So everything is clean, and the response of the crystal to the deposition is fairly quick. But if you give too much iron, some of it remains in the direction of the deposit on the edge of the crystal and can apply a pressure on there and can in fact give rise to this kind of distortion that we now see in the palladium crystal. So we can, I don't think we have to retract this paper or anything, but I think we can now say, give a better explanation as to where this distortion is coming from, where the iron is actually not dissolving into the crystal, but is actually staying on the outside and applying some sort of pressure on the surface of the crystal, and we see this response of the crystal to it. Okay, that would be a good time for questions if anybody would like to chime in, because I'm going to talk about phasing for the rest of the time.
Looks like not.
Okay, everyone's asleep.
No, I'm here.
Okay, do we still have 60 people?
Yes.
Okay, very good. Oh, Ian, hi. All right, so now we're getting into some of the gory details, and so this is I just wrote this an hour ago. This is a very glib summary of where we are with the phasing methods for BCDI. So it works well for nanocrystals, and we've got lots of, I think, believable publications of results that we can get with the excellent beamline facilities that we have and the current phasing methods. And as Ross always reminds us, you need good data to get good images. And we see that in the reproducibility of the images. You get a bigger variation of images if you have bad data. And good data usually means clear fringes indicating facets. And we have, I think, a good choice of different algorithms and several good compilations of these into packages that we can use. And we're basically trusting that by oversampling the data, we have more data points than we have pixels in the image, and so we can expect to get a unique solution. Okay, so then when the problems start arising is when we have what I call phase domain structures, which are structures where there are blocks of material inside the crystal domains, which are shifted relative to each other. And this can arise due to stacking faults or impurities or sometimes basic physics phenomena such as charge density waves and so forth inside materials. And these give, characteristically, they give multi-center diffraction patterns. That means instead of having one bright center of the diffraction pattern, you get several centers, and they are different. The centers are offset in this sort of random way that looks like speckle. And so when you go from nanocrystals to phase domain structures, you go from these clear single center fringe diffraction patterns to speckle patterns. And the speckle patterns are still a big problem. They result in non-reproducible solutions. With every time you run it with different random numbers, you get a different solution, often similar. You can often even say that we're seeing the same thing over and over again, but not identical. And there are sort of theorems in crystallography that might explain. There's a thing called merohedry, which sort of claims that you can have similar diffraction patterns from different features in a crystal without a unique mapping. And so there is a possibly fundamental uniqueness issue associated with these phase domain structures. So this is where we still have to go in the future. Okay, you may think this came from another speaker, but I put it in quite deliberately. This is what's going on inside every one of your heads right now. The way that you process visual information is in your visual cortex at the back of your brain. The eye is down here. This is the forehead of your brain, and the optic nerve runs through here to the back of the brain, and then feeds into this very clearly layered structure of neurons. And so you have these layers of neurons which undergo the visual processing of the information that comes into your into your eye, and allows you to, in very, very quick time, detect when someone's going to whack you or something like this. So there are defense mechanisms in the brain which recognize patterns of visual information that are coming through this layered structure. And this is it's called the neuronal network in the brain, but the neural network idea is very hot in computer science right now. And this is the one that we've been working on, and the first paper just came out. What we're trying to do here is to do this inversion, the phasing problem, by taking input diffraction patterns and getting out images, amplitude and phase images, using a neural network. And the way we've constructed it is this is certainly not our invention, but this is a very standard method. But it is, as I tried to indicate, based on the neural processing system that goes on that has evolved on its own in human and all animal brains. And it involves this layer-wise processing where you reduce the image gradually to smaller and smaller sizes, but extend the depth of the information. So you're not throwing information away when you go through these steps of coding of the image. You can look at the dimensions that we used in our first study here. This is a two-dimensional neural network which looks at a two-dimensional diffraction pattern and produces a two-dimensional output images. And so we have to, in the decoding stage, we have to expand it back out again into two separate channels, one for amplitude and one for phase, and then combine those together. We have asked if there is a complex version of the packages available. They're not yet available, but maybe one day they will be available, and maybe we can do this all in one flow. But one of the reasons this is very popular now is that the computer hardware that's available with GPUs is actually very well suited to these processing operations. So what you're doing is massive amounts of matrix multiplication that is going on in these coding steps. So you reduce the size from 64 by 64 to 32 by 32 and double the number of depth channels in order to do that. Every one of those has a coefficient associated with it. So there's about 1 million coefficients associated with all of this encoding. But by doing it in layers, you introduce nonlinearities, so that this actually represents, I think if I'm correct, it's a fifth order polynomial mapping of every of the input data onto this fully compressed block in the middle before it gets expanded again. So it builds in the nonlinearities. Okay, if you ask detailed questions about this, I'm going to have to bring Long online to answer those. But just a few key points here. We use a package called PyTorch. The most common one is called TensorFlow, but as far as we know, they should both behave the same. The other thing to note is that there's no Fourier transform included in this. So this neural network is somehow replacing a Fourier transform in the calculation. So there's no formal Fourier transform here. And that has a bonus that the phase is not limited to the phase of a complex number, which is 0 to 2 pi. So in fact, the phase can go beyond 2 pi if it wants to. The other very important thing, which Ross pointed out, he wrote a cover story for our paper in IUCRJ, is that the processing involved in actually, once you've trained this network, you've got all these coefficients stored in a big array. The processing is extremely quick. This is microseconds or so of computation once you've programmed this thing correctly. But as I'll show in the next slide, to determine what all those coefficients have to be, you have to train the network. And so the training takes a very long time, several days for us. But once you've trained it, you can get an immediate replay of any diffraction pattern you like into images. So this could be used in real time with an XFEL, for example, so that you could look at stream diffraction patterns coming in and generate real time, very fast images once the programming is taken care of.
Ian, the Richard Sandberg here. That's two-dimensional diffraction patterns, not three-dimensional?
Yes, I'm going to talk about three-dimensional later. So perhaps you could ask later about that. But we started with 2 dimensions, just looking at a single slice of a diffraction pattern, expecting to get a projection image of that object, and it works, as you'll see. Okay, so we had to do the training. We used about, I think it was 40,000 simulated nanoparticle objects to do the training, and we introduced about 15 parameters that were all chosen from random number distributions to generate a broad range of different sizes and shapes. And one of the nice things that Long came up with is this super ellipsoid function that transforms continuously from a cube through a sort of sphere to an octahedral kind of shape. And we took these with all random orientations, and we also introduced phases to this. I won't show the phase part, but we put in a general kind of phase function and chose random numbers for the phases as well. So not pointwise random functions, but smooth varying phases with a couple of oscillations on the size of the crystal. And used all that to train up the network to get those coefficients optimized. And then we generated some more objects and did tested those same kind of objects, but we tested them unseen by the network. And we could give, these are 6 different inputs for which the shape is given as the second row. The third row is the output of the network, and you can see it does quite well on the shapes and the orientations in all of these cases. And then the phase also comes out quite well in all cases. So we're getting quite close. But there's still a significant chi-square difference between the object that comes out and what is put in at the beginning. So we decided to go a little bit further. Maybe it's a cop-out, but we decided to use the output of the machine learning to feed into an iterative phasing, and we found that it actually gives a significant improvement to the iterative when we do this. So this is an unseen diffraction pattern, and this is the phase, this is the amplitude, and we can extract a support from that just by thresholding the amplitude, and then use that support in a iterative phasing procedure. So you need to focus on this bottom right picture here. So this shows what happens if you just do these are iteration. This is all iterative phasing, but if you just start the iterative phasing from random numbers with no machine learning, you get this sort of response. The chi-square drops to a good number. This is perfect data, so chi-square should be 0 if it's a perfect fit, but it seems to hang out at about 10 to the minus 4. One of the referees suggested we should look at this other computational method called the nearest neighbor search, and we did that. And the nearest neighbor search improves things somewhat, half an order of magnitude or so, but still doesn't come anywhere as close as using the machine learning. So when we use the machine learning and random, so we just take the support from the machine learning, feed that into iterative, the support is already getting us significantly better. The shading is the range of different solutions from different random numbers. And if we use this solution from the machine learning to seed the algorithm, we get the orange curve, which gives us the lowest chi-square of all. So if you seed it, if you use the support and the image from the machine learning to feed into iterative, then it gives the best performance. So we can use this as a pre tool to start off the iterative phasing. Okay, you should be interested how it does with real data. This is a single slice of a barium titanate diffraction pattern that's shown on the left here, and the B and C are the output of the machine learning directly in 2 dimensions. If we then take that support that comes from that and feed it into iterative, we get a decent chi-squared solution of that projection of the barium titanate crystal that's shown down here. Okay, so Richard's question. We now go to 3D, and this one is not yet published. We've actually submitted it 2 weeks ago, so it's you know, I think it's in a state that we're happy with, that we want to present it, and I hope you'll be impressed with the results. So here, what we're trying to do is to encode a 3-dimensional diffraction pattern of a nanocrystal and get a 3-dimensional image of the crystal coming out. So it's just a bigger version of the same thing. We use 4-dimensional arrays instead of 3, and we go down through these coding steps and then decoding steps exactly as before. 2 channels, one for amplitude, one for phase, and then combine them together to give a 3D image. So this is just an extension of what we did before in 2D. This is the response to unseen data from a training data set using a similar model to what we had before. So we've got this super ellipsoid shape, and the ground truth, the shape that was expected, given that we calculated it, is this one, and then the output is coming out resembling quite well the ground truth. But again, there is still some significant chi-square between what comes out from the machine learning and the actual. This is for ideal data, so we know what the answer should be, and there is still a difference between the two. So we actually built on that and extended it a little bit. So this is going into some of the details of how the training is done in the neural network, and this is all classical neural network package kind of material. So what the neural network looks at in order to do the training is this thing called the loss function, and it's basically a kind of fancy chi-square, but it has to obey some rules in order to work correctly in the packages. And what we use during the training, which is called supervised machine learning, is we give it a chi-square between the amplitude of the object that it's generating and the amplitude of the truth amplitude that is coming from the simulation. So we know what the answer is, and so we can work out how far the current epoch of the training is away from that. We can do the same with the phase, and these usually have equal weight, and they're expressed as chi-squares in the formation of this loss function. And then we also use the agreement between the diffraction and the Fourier transform of the image which is coming out. So we're using, in order to calculate the loss function, we are using a Fourier transform in order to get this comparison of the diffraction. And what we found was slightly preferable was to use, instead of the chi-square, we use the Pearson, which is the correlation coefficient, and 1 minus that is a number that goes to 0, so it's a suitable loss function. Okay, so where we went beyond that then is, is to go to a second step, which is to try to refine, using machine learning, the image that comes out of the trained machine learning in a second phase, which uses unsupervised machine learning. And that's based on the second loss function, which isn't allowed to look at the answer because it's unsupervised. And what we found was important was to use both a chi-square, which is sort of, in computer language, it's a bit like the L2 norm difference between the two sets of data, and the Pearson, which is like an L1 norm because it's linear in the amplitudes, not quadratic. And using a mixture of these, where we can actually ramp the coefficients to weight, what we find is we want to weight the Pearson at the beginning and then the chi-square at the end of the refinement. So we're using this unsupervised machine learning to refine the solution that comes out of the supervised machine learning. And this is showing that it works. Here's now unsupervised learning. If we use the pre-trained output of that trained network, we get a very good image coming out at the end, and the trajectory is the green curve in panel E here on the right, where we get down to a decent loss function, or chi-square if you like. Lot of cycles of the machine learning. But what we found was also true, and this was a bit of a shock, and in fact this is a question to the audience as well, is that even if we did not train the network, if we just started with, I go back here, if we just take all these million coefficients of to random numbers and just run that purely unsupervised without any training at all, we get the purple curve. So it's a little bit slower. It takes a little bit longer to respond. But basically this middle column here shows the result, and it's basically indistinguishable from the one where we use the training. And so long as you've got enough time on your computer to run this, you have to run it a little bit longer. You don't even have to train it in the first place. So you just do this unsupervised machine learning, and you go directly from the structure of the neural network, you get an image of a nanoparticle, and that's a little bit shocking, that you don't even need any training for that to work. Okay, so we've applied it to 4 different experimental sets of data on nanoparticles. Just to tell you the background, the strontium titanate was synthesized by Anna. The barium titanate was a commercial sample that we were able to buy. The palladium was, this is a different sample from Frank Sung, and the gold was made by Ross, I think. I think it's the standard one on the wall of the hutch that we looked at. So this is the standard sort of gold nanoparticle. And the palladium, as we saw earlier today, it has this octahedral shape. The gold has a little plate shape. The barium titanate has a faceted shape with some interesting sort of rounded edges to it. And the strontium titanate has a cube shape. And all of these are done with this completely unsupervised learning. I think this one was using the training, but as I just told you, we can't tell the difference, and I'll develop that a little bit in a moment. So we can reproduce the diffraction pattern extremely well, and we get a respectable looking shape with amplitude and phase. This is 150 nanometers in each case. So these are all sort of 200 nanometer sized crystals, but all of them work well. And if we look at try to compare what you get with the iterative method and the machine learning method, we're slightly ahead with the machine learning, but this is a little bit subjective because the iterative has to have a support, or else it isn't even meaningful. And so we do use shrink wrap for this, and I don't go into those details here. But if you just look at the raw chi-square, we get comparable chi-squares with, this is for the strontium titanate data. You get comparable chi-squares, slightly narrower distribution with the machine learning, but in both cases, because it's starting from random numbers, you still get a distribution because there's noise in the data. And but if you look at the scale, this is actually not a very wide scale of chi-squares. And if you look at the Pearson, because we did use that in the machine learning, we don't use that. Well, to be honest, and I meant to make this point earlier, neither the iterative does not ever look at a chi-square. It just runs the algorithm for self-consistency between real and reciprocal space constraints. And the chi-square is just a measure, independent measure of its success. In the case of the machine learning, we're actually driving it with the chi-square and the Pearson. And so that one, Pearson does come out a little bit better for the machine learning. But if you use a different shrink wrap threshold, then the number for the iterative is going to change. So it's for illustration. We're not claiming one is better than the other at this stage. So what you should be wondering, what I was very concerned about, was actually look. And so I've got a few slides showing some comparisons, all for the strontium titanate, but these are showing cross sections of the amplitude and phase for the machine learning solution and for the iterative solution. And they're both basically the same chi-square. And this was the shrink wrap threshold that we used to get this one. And the shapes are basically the same, but not identical. So I would say that the there is more fluctuation of the amplitude in the iterative image than there is in the machine learning. That may be good, fluctuation is real, but we don't know, and so we just have to just say that's what's happening. And both give the same phase. The border of the phase is sort of meaningless because when you don't have any amplitude, the phase doesn't mean anything. So they come out a little bit different. This one's cut off by the support. This one, I don't actually know why it's cut off, but maybe Long can answer that. Okay, so here's another one. This is a figure we're including in the paper. This shows on the top the supervised and unsupervised machine learning images for the strontium titanate, and the bottom 3 typical outputs from the iterative. And you can see they're definitely not the same. You sometimes get little corners missing. It also illustrates quite nicely this point that the phase wraps with the iterative but does not wrap with the machine learning, because there's no Fourier transform in the machine learning. It's just finding the solution. And then this was something I put together trying to show that this was a single data set fed into the machine learning, and the same data set fed into iterative, where it really did not reach a good solution at all. And maybe I didn't do enough iterations, but basically it came out too small. If you give a merge of 6 data sets, you get an image which is comparable to this one, but the machine learning one sort of looks a little bit crisper, a little bit more sort of believable perhaps than even the one with more data added to it using the iterative. I also made this one where I looked at more cycles of iterative, so 1,000 cycles and 2,000 cycles. Again, always giving the same chi-square, and you can see phase wrap type features sometimes appear, but you also definitely see lopped off corners and quite bad reproducibility. Whereas actually, I may have the labels backwards here. I think the training one might be on the left, and okay, but anyway, these are the 2 different versions of machine learning based on training or without training, and you get some variation of the images coming from the machine learning, but generally the shapes, to my biased eye perhaps, tend to be a little bit cleaner for the machine learning than they are for the iterative. So we may be gaining here with the new method. Okay, so I've used up my time. Actually, I've gone over an hour, have I? Okay, well, hopefully people have not completely just gone away. Anyway, so this is just to wrap up. Where are we going next? First thing I want to know is why the unsupervised learning works at all. Why just the structure of a neural network is enough to solve the phase problem for a nanoparticle, because none of that is ever put in. It's just a neural network with a diffraction pattern and nothing else that's given to it. Yet we're getting respectable looking images, possibly better than the iterative method. We need better metrics to judge what the quality of the output is, and we probably need to, coupled with that, we need to improve the tuning of this loss function. So one thing we can add is we can force the image to go to the center. We can put in some of the ideas of shrink wrap, that we want to have a compact kind of shape to the object. We can also put in sharpness of the edges and flatness of the amplitude as criteria in the loss function to drive in that direction, because the unsupervised machine learning is just a simple optimization process. And then we want to turn to these still unsolved problems of phase domain structures, and even beyond that, there is the issue of when you use a pinhole to light up a piece of large sample, and you get a speckled diffraction pattern from that, we would like to be able to even solve those inversion problems, but that's for the future. So Russ suggested I put this in. This is what we were measuring last night. This is an example of a phase domain structure where you get a lot of speckles. There's a Bragg peak, there's a general Bragg peak, but there's no single center to that Bragg peak. It's a strongly speckled diffraction pattern with well-defined edges, but no proper center. Okay, I'd better stop. I talked obviously too slowly because I ran, even though it was only 40 slides, I ran over an hour. Okay, so that's my summary. We're good on nanocrystals using the iterative methods, and we've got the potential of being able to go beyond that using machine learning, which is currently doing as well, possibly better than the iterative methods. So thank you, and please, if you're still there, give me some questions.
Okay, great. Thank you, Ian, for a very nice talk. There is already a discussion going on in the chat.
Okay.
I don't know, some people answered the question, but the first question was related to the physics included into the process of unsupervised learning.
Yes.
Like if mathematically the forward process can be anything, not even the Fourier transform. So Jiang is curious, how does it knows the physical process, the forward Fourier transform it should inverse?
That's correct. I'm still baffled by that. That's why I wrote that as a future question. We may get it from the referees. By the way, many of you may be the referees of this just submitted paper, but so I'm feeding you with things to attack us on. But basically, the fact that this works unsupervised means that the structure of the neural network is actually responsible for learning how to do a Fourier transform. So the Fourier transform must somehow be built into this. And that was actually why I showed the picture of the visual cortex ahead of time, because some of those processes that go on in your brain, which are inside the structure, this layered structure of the neural network, is a little bit like, in fact, if you look at the Cooley-Tukey, the way an FFT is actually done, it's done as a set of permutation steps in the arrays in the image, and there's only actually one complex number that goes into the and so I suspect that there is some similarity. I can't put my finger on it yet, but there's some similarity between this structure and a Fourier transform.
Hi, yeah, this is thank you for explanation. So just to follow up your question is follow up your answer is I feel like you mean the architecture of the network itself implies it's a Fourier transform to the inverse.
Yeah,
is that correct?
Yeah, I believe so, and I'm saying that informally because I can't prove that. But if you look at how an FFT works, it does have a little bit of the same structure as this neural network structure that's given. But our result is quite shocking, which is you give it diffraction patterns, you give it no training at all, just random numbers, and it's able to figure out the object is coming out. Now, to amplify that a little bit, there is a support sort of in there. And the reason is because the data is 64 by 64, the output is 32 by 32. So we don't go with, the output is smaller than the input. And so that implies that the object has to fit inside a smaller array. So there is a little bit of that built into it, but by no means any, any formal Fourier transform.
Okay, thank you.
Right. There is really a lot of questions going on. So I think Jesper was the first. Do you have to do the machine learning for specific experimental geometry, energy, and pixel size?
The answer is no.
Training, I guess.
The training, no. It's just looking at the Fourier transform part. And as I think the people that do this know, what we usually do is we do our are inversions in detector coordinates. So we take some distorted picture of the object in detector coordinates and find the image in inverse detector coordinates, and then do a coordinate transformation to go out to put in all the wavelength doesn't even go in until that final step of projecting out the object into XYZ real space coordinates. And we do the same here. We do the machine learning in detector coordinates and then project out to the lab coordinates at the very end.
All right, thanks. I think Ian was the next. You can unmute yourself.
Thanks, Dimitri, and hello, Ian. Great stuff. I'm reminded by these questions of how things were discussed in 1999 and 2000 when John Yao first presented reconstructions of this A, B, C, D, E, F test pattern, if you remember. And everybody was amazed, how could this possibly work with just a constraint? But my question is, have you uncovered problems which just do not appear to be solvable or which are pathological for the ML approach?
Yeah, we think that the subject's fairly hot, and so we really wanted to get a paper put together, but I have a list of many, many pages of things that we still have to try. And very near the top of the list are the phase domain structures. And well, to be completely honest, I have thrown them into the current algorithm and they don't work. So you don't get reproducible images with those phase domain structures. But that's probably because well, number one, we have to come up with a better loss function that somehow puts in those features into the structure of the way that the machine learning takes place, or we have to, come up with some other way of simplifying the problem so that it may have a chance of working. And obviously we can do tests with simulated structures that are not so complicated that we can find out when it fails and so forth, so we can deliberately break it in a controlled way.
Perhaps very non-compact structures, for example.
Yeah, for example, yeah. So anything split into two things, that's probably going to be a big failure already. But it's something to learn from. So yeah.
Thank you.
Okay, thanks. Before everybody is gone, I want to make a small advertisement that specifically the machine learning algorithms now getting attention in another webinar by Julio Cesar da Silva from Neely Institute. I will just put the link in the chat about this workshop, and if you're interested in machine learning approaches for X-ray imaging, please go there. And the next question will be from the Carlos. So, yeah.
Hi, thank you, Dimitri, and thank you, Ian, for the presentation. It was very, very nice. So you answered one of my questions already. The other question I had is, I saw a lot of works on using machine learning for actually trying to solve data that is poor quality data, basically because they have a lot of noise, and then you would kind of denoise it and try to do it. Have you managed to do some experiments to see if that would help in that sense?
No, in fact, we've mainly focused on the best data we can get our hands on. But we do have four examples in the current paper, and they are quite good quality data in all cases. Possibly the weakest of them is the palladium, but we haven't looked in much detail at the noise sensitivity. What we think happens is that the distribution of chi-squares just gets wider and wider the more noise or the worse the data that you put in is. But at some point it fails completely, and exactly what happens when it fails completely, we don't know. There's other sort of detailed answers to that question. One thing that I do quite often, and I haven't evaluated plus or minus, is I can go in with image J and I can remove bad pixels from the data. So you can just do a veto type removal of bad pixels. And we also remove aliens and things from the data because we know where they come from, and we know that that's not part of what we're trying to study. And every one of those steps has consequences down the road if you then put it into machine learning. So there are steps which I would steps that are worth doing, and we do them anyway. But whether that could all be part of some giant big machine learning system one day is a big question.
Okay. Thank you.
Thanks. The next question from Anastasios.
Hi, Dimitri. Thank you.
Hi.
Hi, Ian. My question is with regards to the relationship between an object and the observed data.
Yeah.
We know it's a Fourier transform, so okay, it makes sense. Is this relationship unique? I mean, is there another function, maybe analytical function, which is not the Fourier transform? And if, let's say, it exists, is there a way that the machine learning algorithm can give it to us? Can we extract it from that?
I think the answer to both questions is yes. In fact, the same question was asked by one of my esteemed theory colleagues, Nigel Goldenfeld, when I gave a colloquium at Illinois when we first started doing this in 2005, something like that. And he said exactly the same thing. He said, why do you only look at Fourier transforms? There are infinite numbers of transformations available. And one that has been talked about quite a lot is the so-called partial Fourier transform, where it corresponds to taking an object and propagating it Fresnel propagating it in space and getting a sort of hologram of that object, partly real space and partly reciprocal space type object. All of those are approachable by the same method. And in fact, the neural network could also be thought of as a sort of propagation algorithm in that sense.
That's exciting news, I guess.
Yeah.
Okay, there are more questions from Annas. Do you have a code repository available for this implementation, I guess?
Let me ask Long about that. If you send an email, we'll think about it. It's not very stable at the moment because we're constantly tweaking it, and it may not be something that we're willing to share. But when we publish the paper, we will definitely make a version available. Our 2D one is already available, and that one we've sort of tidied up enough that that's something we can distribute if you send us an email. But the 3D one, until we get it published, we probably don't want to be sending it out.
Good. The question by Pablo, I think it repeats the noise question. I don't know, Pablo, if you're satisfied with the previous answer. I guess yes.
No, I wanted to add another comment. I mean, regarding the unsupervised and the untrained one, we've been also playing with that in the near field context, not in the far field one. And we saw that it was extremely sensitive to noise.
Okay.
So, yeah, have you been playing with that, and do you have the same experience in far field?
We have not been playing with any near field yet, but we, like I said before, we would expect it to work in that situation. Why it would be, if you're suggesting it's more sensitive to noise in the near field than the far field,
No. I'm not suggesting it's more sensitive to noise. I mean that so if we compare to the traditional supervised, or the pre-trained models, even if they're unsupervised, when we go to this untrained and supervised scenario in near field, we are always working in near field ourselves. We saw that we were much more sensitive to noise, and sometimes we were getting crazy results that didn't make any sense.
Yeah.
I mean, I was asking if you have the same experience in far field or not.
We haven't looked at it very systematically. So one thing on our list is to deliberately add noise to the simulations, because there's different ways to do it, and it needs to be done carefully. We were in a rush to try to get quickly. And again, if the referees jump on us for that, then we'll have to take a look at it. But it's definitely going to get looked at. But partly an answer is that it works already for experimental data. So that is inherently noisy at the level of 1% or so. And it might be that the noise is structured in some way, but 4 out of 4. I mean, we haven't had any. Well, yeah, okay, we've got four good examples, and that was our original choice of good data, and all of them worked. So we were pretty happy about that.
And regarding your comment, this approach that then supervise and untrain, this is known in computer vision as deep image prior, and there are several papers last year from that. I mean, they are doing for dephasing in near field, but
yeah,
they can also apply to far field trivial.
Yeah. I've also been reading, listening to talks about things like regularization of the loss function, which involves going to an L1 norm instead of an L2, and that might be actually quite important. But I'm learning this completely. Long is much more knowledgeable than me, but you know, it's a very big subject in the outside world. So there is a lot of information to gather. If you could send me the paper, that would be very helpful.
Yeah, and also we have some others regarding if you use L2, L1 norm, if you go to the average or the median of your solutions.
Ah, okay, that's interesting. Yeah. Yeah, we definitely needed both L1 and L2 in our unsupervised. And we switched from mostly one to mostly the other during the epochs.
Okay, yeah, that's really interesting. I never considered that. Thank you.
Well, there is a sort of logic to it, which is that the L1 is sensitive to the weak data, the outer fringes, and the L2 is mostly dominated by the strong center of the diffraction pattern. So that's why we included both.